Why is it that we are here made of matter and not antimatter? Let's embark on a journey into the depths of particle physics and cosmology to explore these questions. Our narrative starts around 13.8 billion years ago with the Big Bang. This cataclysmic event, according to prevailing theories, produced equal amounts of two intriguing entities, matter and antimatter. Now, matter is what we're familiar with, the stuff that makes up everything we see, touch, and feel. Antimatter, on the other hand, is like matter's mirror image, possessing opposite charges. Take an electron, for instance. This negatively charged particle has an antimatter counterpart known as a positron, which carries a positive charge. These counterparts, despite their opposing charges, are nearly identical in every other way. However, their relationship isn't one of harmony, but of annihilation. Upon contact, a particle of matter and its antimatter equivalent will destroy each other, releasing energy in the form of light. It's a spectacularly destructive dance, and yet it's fundamental to our story. Because if the Big Bang truly produced equal amounts of matter and antimatter, they should have annihilated each other entirely. The universe, as we know it, should be a void, bereft of matter, but as we can clearly see, it isn't. The stars, the planets, the galaxies, and indeed we ourselves are proof that matter prevailed. Intriguingly, despite the equal production, we live in a universe dominated by matter. Why is this so? Why didn't all the matter and antimatter just annihilate each other, leaving nothing behind? What tipped the cosmic scales in favor of matter? These questions lie at the heart of one of the most intriguing puzzles in physics and cosmology. As we dive deeper into this mystery, we'll explore theories and experiments that seek to explain this fascinating asymmetry between matter and antimatter. When matter and antimatter meet, they annihilate each other, so how did matter survive? A perplexing question indeed, and one that takes us to the heart of a cosmic mystery. Let's take a step back and understand what exactly happens when matter and antimatter collide. Picture two cosmic dancers, one representing matter, the other antimatter. As they approach each other, they are drawn into a dance of destruction, a process known as annihilation. In this destructive dance, both matter and antimatter disappear, their energies released in a burst of light. A beautiful but deadly spectacle. Now, if the Big Bang, which happened around 13.8 billion years ago, created equal amounts of matter and antimatter, then they should have danced this dance of annihilation until none were left. But here's the twist in the tale. If that were the case, our universe should be empty, a vast expanse of light with no stars, no planets, no life. Yet here we are in a universe teeming with matter. So what happened? How did matter survive this cosmic dance of death? This is where we encounter the concept of asymmetry. For reasons we are yet to fully understand, there was a slight imbalance in the early universe. Picture a cosmic scale with matter on one side and antimatter on the other. In the beginning they were equal, but then for some reason still unknown, the scale tipped ever so slightly in favor of matter. This tiny imbalance was enough for matter to survive the dance of annihilation. But what caused this imbalance? Could it be that the laws of physics favored matter over antimatter? Or was there something else at play? The quest to answer these questions has taken scientists on a journey deep into the world of particle physics and cosmology. The survival of matter over antimatter introduces us to a fascinating concept, CP violation. This concept suggests that the laws of physics might not be the same for matter and antimatter, leading to a preference for matter over antimatter, but that's a story for another scene. For now, let's marvel at the cosmic dance of annihilation and the mysterious asymmetry that allows us to exist. CP violation, a slight difference in the behavior of certain particles, may hold the key to our existence. Let's delve into this fascinating concept. CP stands for charge parity. In elementary terms, it's a symmetry principle between particles and their antiparticles. But what does this mean? It's the idea that if you were to swap each particle in the universe with its antiparticle, its mirror image, and then look at this mirror universe, it should behave exactly like our original universe. However, this is where CP violation comes into play. It's a little like finding a chink in the mirror in certain conditions. Some particles, such as K-mesons, behave slightly differently than their mirror images. This is the violation of the CP symmetry principle, a subtle but significant difference in the behavior of some particles and their antiparticles. And why is this important? Well, this violation could be the reason why matter prevailed over antimatter. The slight preference for matter over antimatter caused by this violation could have led to an excess of matter in the universe. This means that the laws of physics aren't exactly the same for matter and antimatter, but how do we know this? Experiments at particle colliders, like the Large Hadron Collider at CERN, have observed this CP violation. They've noticed it in particles containing strange and bottom quarks. These findings imply that similar processes might have happened in the early universe, tipping the balance in favor of matter over antimatter. So, while the universe might seem symmetrical at first glance, a closer look reveals an intriguing bias towards matter. It's this fundamental asymmetry that's at the heart of our existence. It's the reason why the universe, as we know it, is filled with galaxies, stars, planets, and us, rather than being a void filled with light from matter-antimatter annihilation. Experiments at particle colliders provide us with clues about this mysterious phenomenon. And with each new discovery, we inch closer to understanding the cosmic riddle of why we exist. Experiments at places like CERN's Large Hadron Collider have observed intriguing behaviors in particles. Scientists have made fascinating discoveries by smashing particles together at high speeds. In these high-energy conditions, particles of matter and antimatter are produced, giving us a glimpse into the early universe's conditions. One of the key findings is the observation of CP violation, particularly in particles containing strange and bottom quarks. This violation manifests as a slight difference in the behavior of matter and antimatter particles. In essence, it's as if the universe has a preference for matter over antimatter, a bias that could explain why we see more matter in the universe today. To put it simply, these experiments have shown us that the laws of physics aren't quite the same for matter and antimatter. These findings suggest that similar processes could have occurred in the early universe. Quarks and leptons, the fundamental particles that make up atoms, play a crucial role in this cosmic puzzle. These particles come in 6 different types, each with their corresponding antiparticles. Intriguingly, certain neutral mesons formed by one quark and one antiquark can spontaneously morph into their antimatter equivalents and vice versa. This fascinating phenomenon isn't a perfect mirror, though. It's not a one-for-one trade. Instead, this metamorphosis occurs more frequently in one direction than the other. Over vast cosmic timescales, this bias in transformation rates leads to an excess of matter. It's as if the universe has a preference for matter over antimatter. This bias, this preference, may be one of the key factors that tipped the scales in favor of the universe we observe today. A universe dominated by matter. Scientists continue to explore various theories to understand this asymmetry better. The quest to understand the matter-antimatter asymmetry is far from over. Today, scientists from all over the globe are investigating a host of theories and conducting experiments to shed light on this cosmic conundrum. Some of these theories extend beyond the boundaries of the standard model of particle physics, venturing into uncharted scientific territories. Others focus on the elusive neutrinos, ghost-like particles that barely interact with matter, pondering their potential role in the early universe's lopsided affair. Researchers are constantly developing new techniques, improving existing ones, and designing more sensitive detectors to catch these elusive particles